Hello and welcome everyone to my first video ever, this time with my own voice, and as you all can clearly hear, English is not my native language, so you certainly found out and will find it out even further when I'm struggling to find words to describe certain topics. But I don't want to be a professional streamer, so this is not scripted at all. This is just a small video trying to show you how I usually approach things like the GreenPAK currently. And GreenPAK is quite an interesting thing because 1 week ago I wasn't even aware that these packs existed, and when I saw in a video that someone is using them, I was heavily interested why and what these little small packages are able to do. And I found out that it's more or less like a small FPGA, including some analog circuitry as well in there. It's quite a mix. But what makes it so special is that it's small, it's cheap, and it's quite heavily configurable. So let's jump right into it. What you see on the screen currently is I just bought some of the SG46620V chips. These are cheap, like 20 cents per piece, and of course you need to have a programmer, but you can buy them together, the programmer, the adapter, and 50 of these for about 50, not even that, it's more like 40 something-ish Swiss francs, so quite cool price. And I opened already the editor, and in this editor you're able to see how it does look like if you have already chosen the appropriate device. So in my case, what you need to do at first is you need to jump into project settings and define the minimum and maximum settings, else you won't get far in that editor. This editor, of course, is downloadable for free from the Renesas homepage. You just need to create an account there, which is all for free. You don't need to have some kind of initial payment or whatever. So thanks for that, cool stuff. And of course, this video is not sponsored in any way. It's just like I experience a lot of fun working with these devices, and that's why I decided to make a video about it. But to be honest, it's just maybe the initial euphoria. Maybe I'm going to be disappointed at a later stage, but currently I find these devices quite cool. So anyway, this is the device I told you, which I'm using. So I need to say, okay, which is the minimum and maximum voltage I'm going to apply. I'm just going with the normal standard values by clicking one time up. So 1.71 volts is the minimum, 3.3 is going to be the typical voltage, and 5.5 the absolute maximum ratings. Temperature, I'm doing the same. So we are in the area between -40 and +85 degrees Celsius. That's it, and there we go. We are ready to create something. What we could do right now is, for example, which is always a good idea to start with, it's like the hello world in digital environments, is the so-called Parity bit checker, which is quite a simple construct. You just count how many bits are set, and if there is an even number, you put a flag on an even output, and if it's not a number, you just to the opposite and set the odd output to true. That's it, quite simple. You just have to use some exclusive OR commands, and that's where we start with this circuit. Okay, this is a special device. It has on the left side matrix 0, and on the right side matrix 1. There are other devices, they have all in one matrix. Why they have split it up that way, I can't tell you, I don't know yet, but it doesn't matter, because we have here on the right side so-called ports, and between these ports, or with these ports, you are able to talk between both matrices. So it in the end more or less like one device anyway. So if we go through, we see we have here pins to be configured. We have here some digital components like an inverter. And then we have a ton of these LUTs. LUT stands for lookup table. These are quite interesting because the lookup tables are able to be an OR, exclusive OR, and NAND, or whatever, or even something you are made yourself up with, which is not really a standard NAND or NOR or something like that, which is totally up to your needs. Then we have different other, like a flip-flop, like a latch. You need to choose if it's going to be a flip-flop or a latch, but you can define it and add it to your schematic. Then you have in this chip 3 analog comparators in matrix 0. Then you have counters or delays. Then you have even a pattern generator in there, and then special components as well, like an analog and digital converter is in there, power on reset, for example. Then you have an SPI connection interface, digital analog converters, etc. And in matrix 1 you have furthermore, these are not the same ones as shown above, these are furthermore digital components which are also able to be used in your schematic. So let's do not talk too much in theory, let's go straight into creating our parity checker. So what we would like to have is, we have now on the left side VDD and GND, so power is already there, so I have nothing done so far. This is the standard if you're starting the program totally from scratch. But we have here now a lot of inputs. In total we have 9 inputs from 2 to 10, and we are going to use now XOR to create a logic array to count the bits set on the input. So we're going to use let's use 3-bit inputs. Why not? Let's use 3-bit inputs. We take 1, 2, and 3 pieces of them. I'm going to place them in these areas, so we are able to connect these three inputs then to that LUT. So this LUT itself, we need to switch here to properties. It's just defined by user. So you either are able to say, okay, we have 3 inputs here. If you go with the mouse overhead, you see in 0 up to in 2. These are here reflected again in 0 up to in 2, and you can change just the output depending on the input. These are all possibilities on the input side, and you can change for each combination what should come out on the output. And this is quite an intelligent editor. For example, if we say this should be an OR, then you have 2 ways to do that. You could say, okay, if it's going to be an OR, then we say, okay, this is going to be 1, this, and this, and this, and this, and everyone, just if there is a 0, we have a 0, and if we have at least one in one of the inputs, it's going to be an 1 on the output. This is going to be an OR, and you see it already changed on the button to OR because it recognized that we are just trying to do an OR. And what we are going to do is we are going to have an XOR here. So that means 3 times 0 is a 0. 1 time a 1 is a 1. Same here. We have 2 1s, and then it's again a 0. There is 1 1, so it's a 1. 2 1s is a 0. 2 1s is a 0. 3 1s is again a 1. So you see even and odd. If we have an even number of 1s or 0s, better said, no 1s, then it's going to be a 0. If there is an odd amount of 1s, then we have a 1 on the output. So if we push apply, the symbol is going to change here. So we're going to do the same with the second here. This is going to be an XOR as well. Apply, and the third one as well. We have an XOR here and apply. So these kind of inputs or outputs or whatever are just called pins, and you can define if it's going to be just an input. Some of these are just inputs, some others are inputs or outputs, or even an analog input or output, which is all 3 definable. But if we're just going to connect here an input with, for example, that pin, it's going to change automatically. So if we go back to that pin, it says now, okay, since you connected it that way, we decided to change this pin to a digital input, but it's going to be a digital input without Schmidt trigger. You can also have it with a Schmidt trigger or not. So let's leave it like that. For me, it's totally fine. No, why not? Let's change it to Schmidt trigger. So apply. Okay, so let's continue. We are going to connect the other pins as well. So first one is connected, then the second one, and this text box is always a bit annoying, but yeah, I saw it. So, zack, and again, and for the last time, there we go. So now we have 9 inputs, all connected to XOR modules, and if you would like to have, you can say, okay, let's change all the inputs to with a Schmidt trigger to be consistent, even here. So, and there we go. Maybe there is another way. Just selecting all of these and changing that, but I'm not aware of, so I'm going through them step by step, which is also working quite nicely, but needs maybe a second more in time. Good. So now we have connected all the 9 inputs, but we have 3 outputs here, so we are going to use another LUT here. So I'm going to put that here. I'm going to say this is another XOR apply, and the same game. So 1, 2, and 3. So nicely done. So we have connected all the 9 inputs to an XOR array, but now we have the issue that we have no pins left on matrix 0, and in matrix 1 we have several pins which could be used. So what are we going to do? We are going to create so on the source side, we are going to use the ports. So we need to get an output port on matrix 0, and we need to have an import port in matrix 1. So in matrix 0, we are going to activate P0, which is an output port, and you see it's automatically creating an input port. And we scroll down here, you see there is an input port activated in matrix 1. So we are going to connect the output here, and what is always a good idea is to name these. So you have the ability here to set the label and say this is going to be our. So what is the XOR going to do? If we have an odd number of ones, this flag is going to be set. So this is our odd flag. So, and grab the wrong one. So there we go. And on the other side, we're doing the same. This is our odd input. And what are we going to do with the odd signal? I would say we would like to have 2 outputs. One of it is just showing us if it's going to be odd, and the other pin showing us, okay, no, it's not odd, it's even. So we need on the output side an inverter, and we could use, of course, 2-bit input LUT, connect both inputs to it and say, okay, if there's going to be 0, 0, then put an 1 on the output, and if there's going to be 1, 1, then put a 0 on the output, and there is never ever going to be a 0, 1 or 1, 0 at the inputs, since both inputs are connected. But if there is an inverter already here, let's use that. So it's wrongly oriented, so let's flip horizontal. And now we're going to connect these, and now we have here the signal for even. Let's use pin 20 and pin 19 as output. So we're going to connect the odd signal to pin 20 and the inverted signal to pin 19. There we go, and that doesn't look nice, so let's put it like that. Let's put here another label and say, okay, this is going to be odd, and here another label which is going to be even. There we go. So, and now comes a bit of a tricky part. We have all done technically. it's going to work like that out of the box, but we would like to test that. And the issue is, if we would like to test that, then it would be nice if I had the possibility to switch somehow input signals to check if really the output is doing that what I'm expecting it to do. And either I'm going to physically attach switches to all these inputs, and then I'm able to check, of course. But if I don't want to lose too much time to put that in a special circuitry and maybe even solder the chip somewhere else to test that, I would like to add here some buttons, but I can't just add labels but no buttons, so this is a bit of an issue. So how to handle that? And the trick here is just go into debug mode and say, okay, I would like to be in a software simulation, say okay. And if you do that, then you are able to on first add here a probe, not just a signal, but you could add a probe here. And if you change the platform, that's the tricky part, not to software simulation, but to the GreenPAK Advanced Development Platform, and you say okay, then you get special input possibilities. For example, you are able to say, okay, I would like to have an LED, and you just click on that, and that means then on the development package the LED is going to light up if there is a 1 or not. You have not an LED on pin 2. This is, I don't know, some restrictions to the hardware. I don't know exactly why, but some pins do not have LEDs attached. But the trick now is if you click on the NC with your right mouse button, you are able to say, hey, I would like to have a button here. And we do that with all the inputs. We would like to have a button on all the inputs. So, and the problem is a button is not enough because it's going to be complicated if you would like to have a special input pattern with 5 buttons pressed. Therefore, we are going to switch that, and that's now possible since we changed to a button. And if you go with the mouse on it, we have the possibility to say, okay, this is not just a button, and with the button key default connected, but it's going to be a latch. So we need to change that as well. It's going to be a latch here. Again, if someone of you is more experienced than me with GreenPAK and there is an easy way to do that, then please tell me. I'm always happy to know. Okay. This one is wrongly assigned as it's a bit of button. So latch. There we go. So now we are able to say, hey, on the input we have a ground or VDD. We can easily switch and it stays like that. Perfect. Good. Maybe, yeah, why not? Let's say we would like to have enable the chip as well. Then let's go out of the debug mode and let's say we need on the output side, because there we have some pins left. Let's say we are going to use there a 2-bit input lot. So, and what we are now going to do is we are going to erase that wire here and that one as well. So now it's going to be interesting. What we are going to do now is, I'm going to move that a bit. So we say, let's connect the signal with that one here. So, and the output is going to be connected with the inverter, and the output is going to be connected with the odd output signal as well. There we go. And now we say, okay, pin 18, we're going to connect this with pin 18, and I don't like that how it's displayed here. I'm not able to pull that down. Come on, doesn't look nice to me. I don't like that. Let's erase that wire. Let's try that again. Yeah. Somehow I'm not able to pull that down. Okay, let's leave it that way. I don't care for a moment. So, pin 18 is going to be a digital input. We're going to say with Schmidt trigger, we're going to set the label and we say enable. So this is our enable. And what I would like to have now is, let's go to the LUT. Yes. And I would like to say, if there is the input signal here is going to input 1. So input 1, if there is a 0, I would like to have a 0 on the output. If there is 1, I would like to have a 1 on the output, but only if the input enable is high. So input enable is on input 0. That means if input enable is high and we have a 0, I would like to have a 0. Okay, fine. If input enable is high and input 1 is high, I would like to have a 1. So if input enable is 0 and we have a 1, I would like to have a 0. If input enable is 0 and we have a 0, I would like to have a 0. So there we go, and it automatically found out it's just like a simple AND. Okay, then it's a simple AND, fine for me as well. There we go. So now we have an output. We have there the possibility. Okay, let's maybe do one thing more. Let's go back into debug mode and say the enable pin here. We are going to use here a button as well, and now I need to scroll over. The button should be a latch, and this one is going to be default true, so enabled. So it's easy for us to check that. Okay, that's it. Now we have two possibilities. We could either check that by using the software simulation, or we can check that by using our hardware device. And now I'm going to attach the camera to my hardware device, and I'll try to program that as well and to show you exactly how it looks like in the system and on the device itself. Good, let's see you in a second. So I just tried to attach my GoPro camera to my development device. I hope it works somehow. Let's go ahead. So if I go back to my software, and I already said that we are going to connect the GreenPAK Advanced Development Platform, so I need to power it on. There we go. Now we see there is an orange light. That means we are connected with it, and I try to start the emulation. So what's going to happen? I need to activate the LEDs, and now we see that we have two LEDs lighting up. These are the LEDs 18 and 19. So why 18? Because 18 is our input here, and the input signal we said is going to be high. So if we're going to switch that, you see, that's working. But what is not working is that, yeah, of course it's not working because I made a mistake. I can't just say, okay, let's put one output here and leave the other one unattended. So we're just going to switch the odd signal off, and the even signal would stay as it is. So perfect. Let's stop the emulation and let's do that correctly. So okay, we are going to delete these wires here again, and this one as well, and this one as well. And now we're going to change that. We're going to use another, let's stop the debug session, another LOT, tac, and this time we're going to switch it directly here to an AND, apply, there we go. And we have an AND here on the odd signal, we have an AND here on the even signal. We are going to attach this, come on, to, oh, sorry, we just set wire, attach this to odd, attach this to even. We are going to put this one here to directly the odd signal. We are going to attach this again to the inverted output, but the inverted output is going to that here, and the enable signal is going to be attached. So took the wrong pin. There we go. So we have 2 times an end and we have 2 signals going out. You see, it's that simple to correct the whole schematic. Let's go into debug. Let's start emulation again. So again, we have these 2 pins lighting up, and if I'm going to toggle the enable here, tuck, you see both LEDs go off. So that's how it should be. So it's disabled, it's off, it's enabled, and it's on. So if you're going to change one of the inputs here, tuck, you see, it's going to switch the output. It's even or odd. Why don't we have an LED on the input side? Because this is the special case, the only input which does not have an LED. Let's use input number 2. Then we see, okay, tuck, we have an odd number, so odd lights up. We have an even number, so even lights up. That means 1 means odd, 2 is even, 3 is odd, and so on. So it's working quite perfectly. Huh? And if we are going to switch the enable off, so we have no output, and then we have back our output. Yeah, that's it. It's so simple, and that's how you program a small FPGA from GreenPAK, and you're already able to use that small device in your circuitry. That's quite cool. I think, at least, it's quite cool, and it opens a lot of doors for me to be even faster and cheaper and more versatile when I do my further schematics. So that's it. Tell me how to work with maybe already GreenPAKs, or if you like it or not, and why you don't like it. But I think this is quite a new and cool invention I wasn't aware of. So that's all for today. Thanks a lot, and have a nice weekend. Bye.